Modern supply chain replenishment is built almost entirely on past performance. Traditional systems operate as a linear feedback loop, setting future inventory levels based on what already happened. To manage millions of stock-keeping units, legacy enterprise resource planning systems rely on rigid statistical clustering, grouping parts together based on historical sales volume. This logic breaks down when faced with a high-volatility, long-tail catalog. Predicting regional demand for a specialized part for a 10-year-old vehicle is impossible using historical averages alone, as the demand signals are too sparse and erratic for standard math. Because legacy ERPs are disconnected from real-time external data, human planners are forced to manually export data into spreadsheets, attempting to bridge the gap between reactive systems and the actual market. This reliance on manual analysis creates a persistent struggle between two financial risks: localized stockouts that result in lost sales, and excess holding inventory that ties up millions in working capital. Solving this requires the deployment of an agentic supply chain, a multi-agent operating system that functions independently of historical rules. This architecture allows an organization to demote its legacy ERP to a headless system of record, while the AI layer functions as an autonomous system of action, making decisions in real time. Simply increasing data storage or running standard machine learning models over the same old datasets does not fix the underlying problem. True planning requires a system that prioritizes current signals over historical averages. We can see this system in action by looking at a high-stakes scenario: a severe winter storm forecasted for the northeastern United States in 7 days. Autonomous planning cannot happen in silos. The first layer, PI Unify, establishes a master ledger by pulling data from across the enterprise. Integration frameworks use pre-built connectors to extract and harmonize transactional tables from SAP or Oracle, pegging them alongside external weather and traffic signals. By utilizing zero-copy federation, the system establishes pathways to existing data without creating redundant duplicates, ensuring that every layer of the architecture operates on a single source of truth. However, a ledger of unified numbers still lacks the context of the physical world. A spreadsheet doesn't know the difference between a truck and a warehouse. The second layer, PI Semantic, solves this by applying a supply chain ontology that defines how these data points interact in reality. This layer translates raw tables into a machine-readable map of entities and relationships, defining constraints like shipping times. This creates a digital twin, a virtual ecosystem, giving agents the contextual knowledge to understand how a decision in one region affects the whole network. Without this semantic layer, an AI might provide a mathematically perfect replenishment plan that is physically impossible to execute due to unmapped real-world constraints. With a digital twin established, the third layer, PI Decisions, takes over. This is the intelligence engine that moves the system from visibility to action. The system uses an agent council, specialized microagents negotiating via standardized protocols. The demand agent, Ron, cross-references storm forecasts with registration data to identify vulnerable vehicles. Ron predicts a 78% probability of a demand spike for engine block heaters. The inventory agent, Cassie, calculates the immediate stockout risk, mapping 3 different replenishment routes.
Alex, the finance agent, overlays the shipping cost and potential margin for each route, filtering options to the single most profitable path. This think, act, observe reasoning loop allows the agents to simulate the outcome of their decisions before any physical inventory is moved. The system runs thousands of these simulations in parallel, stress testing the replenishment plan against potential shipping delays or further weather changes. Essential Moderator Agent synthesizes these simulations, resolving the conflicts between inventory needs and financial constraints to create a single consensus plan. This negotiation is what makes the architecture resilient. It ensures that every decision is vetted for both operational feasibility and financial impact before it is finalized. Giving an AI control over multi-million-dollar inventory movements requires absolute security. No organization can risk an autonomous system acting outside of corporate compliance. This is the role of the fourth layer, PI Shield. It acts as the governance kernel, providing a transparent, glass box environment for every decision. PI Shield explicitly separates the AI's reasoning from the underlying data, ensuring that the logic behind every recommendation is visible and auditable. Every action is recorded in the AI decision ledger, an immutable log documenting the specific intent and logic used by the agent counsel. This provides a complete reasoning path. The system can trace any transfer decision all the way back to the original weather signal and simulation results. This architecture elevates human planners to the role of curators. They maintain oversight of the autonomous engine, with the power to manually override the system. Without this ledger-backed transparency, the risk of an AI making unverified autonomous decisions would be too high for any enterprise to adopt.
To achieve true autonomy, the system must do more than recommend a plan. It must execute it by writing that decision back into the legacy system of record. This happens at the final layer, PI action, which manages the technical writebacks required to fulfill the agent's decisions. Securely bridging the modern agentic layer with a legacy ERP requires a zero-trust security model. The system generates a just-in-time token, a short-lived cryptographic key authorizing one specific transaction and nothing else. This token allows the execution layer to take the consensus plan and write the specific purchase order directly into the ERP. Once complete, the token dissolves and the pipeline locks shut immediately, keeping the attack surface small. This completes the loop. The legacy ERP remains the system of record, but actual operations are now driven by an external, intelligent system of action. This 5-layer stack is more than just a technical upgrade. It provides a direct, quantifiable impact on an enterprise's bottom line. The scale of this impact is defined by the 2-10 framework. This correlation is driven by the system's ability to process vast numbers of external signals that manual planners simply cannot. By replacing reactive rules with agentic negotiation, organizations see an average 10% drop in planning error. Reducing this error protects against missed sales and excess markdowns, unlocking a vertical revenue increase of 2%. Companies recapture this revenue by fulfilling demand that was previously lost to stockouts and by protecting margins typically lost to forced markdowns on excess inventory. Layering this operating system over existing frameworks transitions organizations away from manual planning, creating a supply chain that autonomously captures margin opportunities at scale.